So in this video is the continuation of examples of principle of mathematical induction. So before we start, if you like my video, please do like and subscribe my channel. Thank you. So our first example is, let A and B be an arbitrary real numbers. Now using the principle of mathematical induction, prove that AB to the power n, that is equals to AN BN for all n belongs to natural number. Now see, let the given statement be Pn. Then Pn is, now solution starts from here. Pn is such that this is AB to the power n, which is equals to AN BN. Okay. Now when n equals 1, now this is again for P1, when n equals to 1, what is LHS? LHS, this is LHS, this is RHS. Value of LHS is AB to the power 1, which is AB only. And what will be the RHS? RHS is A1, A to the power 1, B to the power 1, which is again AB. So as you can see, LHS equals RHS. Thus the given statement is true. So the given statement is true for n equals 1. So this implies P1 is true. P1 is true. So now again let Pk be true. Let Pk be true. Now see, then we can write Pk such that A B to the power k equals A to the power k B to the power k. So this will be the statement Pk. Okay, now again we have to substitute that k by k plus 1 means we have to prove that statement, which involves k plus 1 instead of k. So starting with this, now you can write A B to the power k plus 1. Now if it is A B to the power k plus 1 means like it was AB to the power k replacing k by k plus 1. So that will be, you can write this as A B to the power k into AB, because by the law of indices this is power k plus 1, so they are in multiplication. So this thing is what? A k B k into AB. Now this whole thing is in multiplication, so we can arrange it like this: A to the power k into A, and this as B to the power k into B. So this will be A to the power k plus 1 into this will be B to the power k plus 1. So this is what? This is again the same thing, but we have replaced k by k plus 1. So the statement Pk plus 1 is true. That is A B to the power k plus 1, this will be A to the power k plus 1 dot B to the power k plus 1. So again P k plus 1 is true. P k plus 1 is true whenever this Pk is true. Whenever this Pk is true. So thus you have to write a statement like thus P1 is true, Pk1 is true whenever Pk is true. Now hence by the principle of mathematical induction, Pn is true for all n belongs to natural number. Our next example. Using the principle of mathematical induction, prove that 7 to the power n minus 3 to the power n is divisible by 4 for all n belongs to natural number. Now see, let Pn be the statement. Now let Pn be the statement. Now this Pn be the statement which states that 7 to the power n minus 3 to the power n is divisible by 4. So is divisible by 4. Again, for n equals to 1, right, for n equals 1, the given expression becomes this will become 7 to the power 1 minus 3 to the power 1, which is 7 minus 3 equals 4. So this is 4, which is obvious, which is divisible by 4. So which is divisible by 4. So the given statement is true. So this statement is true for n equals 1. That is, P1 is true. So this P1 is true. Now let Pk be true. So this let Pk be true. Now we can write Pk, this is actually 7 to the power k minus 3 to the power k is divisible by 4. Now if this thing is divisible by 4, so you can write 7 to the power k minus 3 to the power k. Now this is equals to 4m. Okay, so what is m? M is any natural number. Now let's start. So this is 7 to the power. Now see, we will replace k by k plus 1. This is 7 to the power k plus 1 minus 3 to the power k plus 1. So this is equals to, now see, now note the step that I am doing now. So this is 7 to the power k plus 1 minus 7 into 3k plus 7 into 3 to the power k. Sorry, this is not 3k, this is 3 to the power k minus 3 to the power k plus 1. See, what I have done in this equation is that I have minus 7 into 3 to the power k and then plus 7 into 3 to the power k. So if you add and subtract any quantity from an equation, that remains the same. Okay, our next step is to take 7 common from this. So if you take 7 common from this, this will be 7 to the power k minus 3 to the power k, plus what you can do is that from these two you can take 3 to the power k common. 3 to the power k common. So this will be 7 minus 3. So on the next is 7. Now 7 to the power k minus 3 to the power k is actually, this is equals to 4m. So we can write this as 4m plus 3 to the power k. Now 7 minus 3 is what? 4. Okay. Now from here you can take 4 common. So this will be, inside bracket, this will be 7m plus 3 to the power k. Now look at the statement. This is divisible by 4 because this is 4 times of any number, which is clearly this is divisible by 4. So our statement P k plus 1, which was 7 to the power k plus 1 minus 3 to the power k plus 1 is divisible by 4. So on the next step you can write P k plus 1 is true. whenever pk is true. You have to write all this what I am saying, that pk plus 1 is true means, so I'm just writing it down, pk plus 1 is true whenever pk is true. pk1 is true whenever pk is true. So thus P1 is true, pk plus 1 is true whenever pk is true, hence by principle of mathematical induction, Pn is true for all n belongs to natural number. That means Pn is true for all n belongs to natural number. Our next example. Using the principle of mathematical induction, prove that n square plus n is even for all n belongs to natural number. So we have to prove n square plus n is an even number. So again our statement Pn, now Pn is the statement such that n square plus n. Now this is what? This is even. Okay, this is even for n equals to 1. Again for n equals to 1, again like see, for again we will take n equals to 1. So n equals to 1, this will make 1 square plus 1, which is basically 1 plus 1, which is 2, is even. So this is even. That means the statement is true for n equals to 1 or P1 is true. P1 is true. Let pk be true. Let pk be true. Let pk be true. Then this pk such that k square plus k is even. Now see, again replacing n by k, k square plus k is even. So now when k square plus k is even, so you can write k square plus k that equals 2m, because for some natural number m. Now see, replacing k again, that k by k plus 1. So this thing, so k plus 1 whole square plus k plus 1. So this is actually equals to, see if you expand the bracket, this will be k square plus 2k plus 1. So let's write it down, k square plus 2k plus 1, and this is plus k plus 1. So this will become k square 2k plus k is actually 3k plus 3k plus 2. So now see, you can do the midterm splitting, otherwise see you can just take this and rearrange it. So instead of again doing the midterm splitting, I am taking this term only, like taking this term only. So this will be k square plus k and plus this will be actually 2k plus 2. So you can take k common, this will become k plus 1 plus 2 common, this will make it k plus 1. Okay, so I think we shouldn't take this thing, because why? You know, k square plus k is actually equals 2m. So you can just write 2m instead of this, 2m plus 2 k plus 1. We didn't require that step because k square plus k is already 2m. Okay, so now from this we can take 2 common. So if we take 2 common, this is m plus, which is k plus 1. So as naturally you can see, this is 2 times of any number, 2 times of this number. So this is an even number, which is clearly an even number. So the statement will be p k plus 1 such that k plus 1 whole square plus k plus 1 is even number. Okay, so p k plus 1 is true whenever pk is true. So again saying thus if P1 is true, Pk plus 1 is true whenever Pk is true. Hence by the principle of mathematical induction, Pn is true for all n belongs to natural number. Next example. Using the principle of mathematical induction, prove that 2n plus 7 is less than n plus 3 whole square for all values of n belongs to natural number. Now you have to prove that 2n plus 7 is actually less than n plus 3 whole square. Now let Pn be the statement. So Pn such that 2n plus 7 is less than n plus 3 whole square. Now when n equals to 1, so you see that, this is LHS, this is RHS. So LHS is actually, this is 2 into 1 plus 7, 2 plus 7 which is 9. Now you see RHS is equals 1 plus 3 whole square which is 16. So we know that 9 is less than 16. So LHS is less than RHS. The statement Pn is true for n equals 1, that is P1 is true. So this P1 is true. Now let Pk be true. So let Pk be true, then this Pk such that 2k plus 7 is less than k plus 3 whole square. Now replacing k with k plus 1. So see, you can write this as twice of k plus 1 plus 7. Okay, now this is equals to, you can write this like this, rearranging 2k plus 2 plus 7. This is 2k plus 7 plus 2. You can write it like this. Okay, so basically this thing is less than k plus 3 whole square plus 2. Why? Because of this 2k plus 7 is less than k plus 3 whole square. So if you replace 2k plus 7, so obvious this will be less than k plus 3 whole square plus 2. Now if you expand k plus 3 whole square, this will be k square plus 9 plus 6k. So 9 plus 2 is 11. So we can write this as k square plus 6k plus 11, because 9 from here, k square plus 6k plus 9, 9 plus 2 is 11. Now you see that k square plus 6k plus 11. Now see, the next step that I am doing, that is important. So if this is also less than, if I write 8 square plus 8, k square plus 8k, means in this I have added 2k plus 5, which will be less than this. Now why I have done this? Because this thing is actually k plus 4 whole square. So k plus 4 whole square is actually, this is equals to k plus 1 plus 3 whole square, because we have to replace k by k plus 1, so this will become k plus 4. So that's why I have done, like made it k square plus 8k plus 16, which is k plus 4 whole square, which is k plus 1 plus 3 whole square. So again writing the statement p k plus 1 says that this is twice of k plus 1 plus 7, which is less than k plus 1 plus 3 whole square. So this is actually 2k plus 1 plus 7. Instead of 2k, I have replaced k by k plus 1. So that means pk plus 1 is true. So again the same thing, pk plus 1 is true whenever pk is true. Whenever pk is true. So thus p1 is true, pk plus 1 is true whenever pk is true. Hence by principle of mathematical induction, pn is true for all n belongs to natural number. Like pn is true for all n belongs to natural number.